Welcome to the EChem Channel. With you here is Xuehang. This video is made for chemistry major undergraduate students who are learning thermodynamics. The first law of thermodynamics states that the energy of the universe is constant. So we know that the universe is an isolated system. So it also means that during any cycling that a system undergoes, the cyclic integral of the heat is equal to the cyclic integral of the work. However, the first law places no restrictions on the direction of the flow of heat and work. So for example, if we have two substances, one is hot and the other one is cold. So we know that heat will spontaneously transfer from the hot one to the cold one, or from the high temperature one to the low temperature one. Another example, if we have a chamber which is separated by a divider, on the left-hand side we have gas, and on the right-hand side is in vacuum. So as soon as we remove this divider, we know the gas will fill the whole volume. So the first law does not tell us why this spontaneous process happened, why the process cannot just go back in the other direction spontaneously. And with the second law, we will understand what determines whether something happens spontaneously, what determines where the equilibrium is, and the direction that process would have to go in order to reach equilibrium. The development of the entropy can help us understand what is the direction of spontaneous change. And because we know the universe is an isolated system, so the second law of thermodynamics tells us that the entropy of the universe is increasing. We will prove the statement of second law in the isolated system in another video. Here, you will first find more descriptions of the second law. During the Industrial Revolution, engineers are trying to build engines and refrigerators. They find it is impossible to make the device perfectly efficient. For example, in the heat engine. So here you get a source of heat, and the heat, can be converted into work in the heat engine. But you cannot convert all the heat into work. The second example is in the refrigerators. In a refrigerator, you would like to transfer the heat from somewhere cold to somewhere hot, from low temperature to high temperature. You will find you cannot transfer all heat from the cold reservoir to the hot reservoir. It means the efficiency is always lower than 100%. The two schematics shown here are the type of machines that violate the second law of thermodynamics and are called the perpetual motion machine of the second kind. And it is never possible to construct such machine. So here are two statements of the second law based on these two situations. Based on the Kelvin-Planck statement says, it is impossible to convert heat into work with a system that operates in a cycle without also transfer some heat to a colder reservoir. So for here, heat QH goes into the system in our engine, and our engine runs in a cycle in the practical use. So some work must come out from the system. And here, because the work is done from the system to the environment, so we have a negative sign here. Then the system must lost some amount of heat, QC here, to the cold reservoir. For heat and cold reservoir, it means you can bring as much as heat you want, and the temperature will always keep constant. Here we would like to describe the process with equations. So for QH, it is larger than 0 because the heat goes into the system, minus W larger than 0 because the work goes to the environment, minus QC is larger than 0 because the heat goes out of the system, and TH, the temperature of the hot reservoir, is larger than the temperature of the cold reservoir. And for the refrigerators, there is the Clausius statement says, it is impossible for any system in a cycle that takes heat from a colder reservoir, transfer it to a hotter reservoir without at the same time converting some work into heat. We can also write the equations for the refrigerators. The heat that transfers to the heat reservoir, negative QH, is larger than 0. The heat transfer from the cold reservoir is QL, larger than 0. And the work is because the work is from the environment to the system, so work is larger than 0. In a heat engine, because the loss of heat cannot be avoided, so the thermal efficiency of the heat engine is always smaller than 1. And we can define the thermal efficiency of the heat engine as eta equal to the work over the energy that costs. Similarly, for our refrigerators, we can define the coefficient of performance for refrigerators as beta equal to QL over work. To help us express the second law, here we will define a very useful but a little bit confusing term, that is the entropy. For a reversible process going around a cycle, if we integral the quantity of the heat of a reversible process over T, we will get 0. We define the differential of entropy as differential of the heat of a reversible process over T. And the entropy is a state function. It means as long as the path is reversible, the entropy only depends on the state at the beginning and at the end of the path. There could be various ways from state 1 to state 2 reversibly, but in order to calculate the entropy, we have to find the reversible path between the state 1 and state 2. And once it is reversible, the entropy change should always be the same. And it is clear that if the process is irreversible, so we have integral dq over t irreversible, it should always be smaller than 0. We cannot calculate entropy from the irreversible process. The term dq irreversible over t is not a state function anymore because we know that heat exchange depends on the path. To help us understand why entropy is a state function, let us see an example here. Assume we have a thermodynamic cycle for ideal gas. On the PV curve, we change from state 1 to state 2. There are two passes. The first pass is an isothermal and reversible pass. So temperature is constant at T1 and delta T equal to 0. When the volume increases from V1 to V2, the pressure drops from P1 to P2. The second pass, we will first go through a reversible adiabatic process. When V1 increases to V2, our pressure is lower than P2. We mark it as P3. The temperature also changes from T1 to T2. In order to reach state 2, we will increase the pressure from P3 to P2 with a constant volume. So let's write the equation for each process. Process 1, because it is an isothermal process, so delta T equal to 0. It means the internal energy, delta U equal to 0. Enthalpy also equal to 0 because the temperature change is 0. And the work equal to pressure multiply dV. Based on the ideal gas law, we say also equal to RT1 dV over V. So then we can get the expression for work as W1 equal to integral V1 to V2 RT dV over V equal to negative RT1 log V2 over V1. Because delta U equal to 0, so the heat equal to negative work. So delta S, our enthalpy, equal to integral state 1 to state 2 dq over T1 equal to R log V2 over V1. Second step, because it is an adiabatic process, so Q2 equal to 0. Then the enthalpy also equal to 0. Step 3, because it is a constant volume process, so delta V equal to 0, and it means the work is 0. Then the heat Q3 equal to delta U3 equal to CV multiply delta T. The entropy of the step 3 equal to integral dq3 over t equal to integral t2 to t1 delta u over t equal to Cv, the heat capacity at constant volume, log T1 over T2. So then, for pass A, the isothermal process, so the enthalpy change equal to delta S1. For pass B, it is firstly adiabatic process, then a constant volume process. The enthalpy change equal to delta S2 plus delta S3. Because step 2 is an adiabatic reversible process, so there is a relationship between the temperature and the volume. So here, T1 over T2 equal to V2 over V1 to R over Cv. So we find actually the delta SA equal to delta SB. From this example, we find that from state 1 to state 2 through 2 different reversible passes, the entropy is the same. So we confirm that the entropy is a state function independent of the path. But the path has to be a reversible path. If there is an irreversible path between state 1 and state 2, we cannot calculate entropy from the path, and the differential of the heat over temperature is always smaller than 0. So thank you for watching the video and see you next time.